Hello guys, welcome back to Maison African Motives, still on engineering science N1, working on dynamics. We've got a question that we're going to focus on from the question paper of July 2022. So we are not going to waste much time. So we're going to quickly rush through the questions that we're given. On question 5, that is 5.1, we are given that John travels by train from Johannesburg to Bloemfontein. The train travels at 112 kilometers per hour. During the journey, John walks to the back of the train at a velocity of 8 meters per second. Graphically determine Jack's resultant velocity. All right. So this is John, not Jack, because all along it was John here. So this is supposed to be John here. All right. So this is supposed to be John's, okay, resultant velocity. Okay. So it's going to depend with the way that you're going to represent this. We are given that is going from Johannesburg to Bloemfontein at 112 kilometers per hour. So the first thing is to convert 112 kilometers per hour. So that's 5.1. So you can convert this to meters per second, okay? 112 kilometers per hour. So we know that we can simply use the conversion to say to meters per second. This is equivalent 1 kilometer. Remember, it's 1,000. So it's going to be 112,000 meters over 1 hour in seconds, because we need meters per second. So if we convert an hour to second, that is 3,600. Okay, so I'm just going to show the screen so that we can have our calculator here. All right, so let's try to divide and see what you're going to have. So we are given that's 112,000 divide by 3,600. Okay, so we are going to obtain 31,111 and so on, which you can just write as 31,111 meters per second. All right. So, or you can use this conversion. 1 meter per second is equal to 3,6 kilometers per hour. So if you are given 112 kilometers per hour, to convert to meters per second, you simply divide these two, you multiply by 1 meter per second. So that's 112 divided by 3,6 times 1 meter per second. So if you divide this, you are going to obtain the same answer. All right. So that is what you are given. Then also we are given that when he is referring back, he is now using 8 meters per second. So when coming back, he is now using 8 meters per second. So this is for going back. He is going back at 8 meters per second. All right. So let's say we are taking this in the south direction. So if John is going downwards, guys, it depends. This question, I want you to understand, guys, it's going to depend with the direction that you are going to work with, because you are not given a direction. So in this case, let's say I'm representing the first direction, which is 31,11 meters per second. Let's say I'm referring to a condition when John is going this direction, that is going downwards. So like I said, it's going to depend with your direction. If he is going downwards, then we are going to have this as 31.11 1 meter per second. All right. Then when he is going back, it means we are going to have now an opposite direction. That is now he is going back this way. At what? At 8 meters per second. So that means the resultant is going to be from this point up to this point here. That is where you are going to have your resultant, from this point up to this point, like this. All right. So like I said, it depends with your original direction, okay? So if we had to use going down, then the opposite, you'll be going up. If you were going up, then the opposite is going to be going down. That is what it's going to be like. Okay, so if this is our resultant, how are we going to calculate this? That's the difference between these two, and is going down. All right, so it is going to be 31,1 minus 8. All right, so if we subtract this one, we are going to have that's 30, 31,111 minus 8, which is going to be 23,11. So you're going to have 23,11 meters per second, and it will be going downwards because here we're going up just by 8. So the difference will be a negative. So this is going to the south. So it depends with the direction that you have chosen in the first place. So please bear in mind, don't confuse this question to say, why have we taken this going down or why something like that. Okay, on 5.2, the bullet of a cannon takes 6 seconds to hit a target 2 kilometers away. 5.21, draw a neat labeled displacement time graph. Okay, that's a distance time graph of the motion. Use a scale of 2 centimeters to represent 1 second. That is for time, 1 centimeter to the 200 meters. That is for the displacement. All right. So this is what you're going to have, guys. We are to draw the displacement. So we need every information. All right. So we are going to take the data that we are given. So the first thing, this is 5.21. We are given the time that was taken, which was 6 seconds. All right. This time was given in seconds. All right. So we're given the time 6 seconds. And the displacement, in this case, we are given our displacement, which is equivalent to 2 kilometers. But remember, this is supposed to be in meters. So kilo, that's 1,000. So we multiply by 1,000, that's 2,000 meters. All right. If we are to check, we have got a scale that we are given 2 centimeters to represent 1 second, 1 centimeter to represent 200 meters. Okay, so let's start with this one for 2 centimeters versus 1 second. So according to time, 2 centimeters is going to represent 1 second. Okay, so this is for time. Then for displacement, we are given that 1 centimeter is representing 200 meters. Okay, so I'm just going to show you a sketch of what it was supposed to actually look like, but you are supposed to draw this accurately. All right, because we have got the given units, the given scale and everything. So remember, this is displacement versus time. So this is our time axis. So we've got our time axis here. Then we move on to the displacement. So this is the axis for displacement. All right, so we are going to have something of this nature in this way. All right, so if we are to take a closer look in this case, we are given our time. All right, so this is our time axis. So this is our time in seconds, and this is our displacement. Okay, that's displacement in what? In meters. So this is supposed to be taken in what? In meters. So take note, guys, that what we are going to do in this case, from the point 0 here, according to time, every 2 centimeters, it's a 1 second, every 2 centimeters, okay? So let's say this is where we are having 1 centimeter, then this is 2 centimeters. So every 2 centimeters, you are going to write 1. So you leave 2 centimeters, that's 1 second, 2 centimeters, that's 2 seconds, 2 centimeters, that's 3 seconds, 2 centimeters, that's 4 seconds, up to 6. So you leave 2 centimeters between each and every point. You leave a space of 2 centimeters, okay? When you refer upwards here, that's you leave a space of 1 centimeter because we are given 1 centimeter is 200 meters. So after every 1 centimeter, it's 2 meters, okay? It's 200 meters. So we're going to have this 200 meters, all right? Up to 2,000. So it's going to be 200. After 1 centimeter, we add another 200, that's 400. After 1 centimeter, that will be at 600. After 1 centimeter, at 800. After 1 centimeter, that's 1,000, and so on, up to 2,000. So you're going to mark these points and so on and so on and so on up to 2,000. All right. So this is what you're going to have at the end. And these points must correspond 1,200, 1,400, 1,600, 1,800, up to 2,000. All right. So marking the points together, because this is going to be 1 versus 2, you mark the points as corresponding, okay? So this 6 seconds, according to time, corresponds direct with the 200. I want you to see this part. So these 2 points, they correspond direct at this point, okay? So they correspond direct. All right, so we're going to have something of this nature at the point of intersection of the 6 second and the 2000. So you can draw a line to join these 2 points, all right, which is important. So the gradient or the change in this is the one that is referred to as the velocity. All right, so in this case, we can just indicate in this manner. All right, from the point here, it must be at the point of intersection like that. Okay, so that is what you can actually represent as your displacement time graph. Okay, so let's check the other part of the question. On 5.22, calculate the gradient of the graph. Okay, so the gradient, which is the steepness of the slope in this case, represents the velocity. That is the gradient, because remember, you are dealing with a displacement time graph. So the gradient represents the velocity. All right. If it was a velocity time graph, the gradient represents acceleration. So you must know this one, okay? So here, the gradient represents the velocity, of which we know that velocity is change in displacement over the change in time. So we can have this as a formula. So that's 5.22. So our gradient, which in this case represents the velocity, is equivalent to the change in displacement over the change in what? In time. So that's the change in displacement over the change in time. So you can take corresponding point, and the best corresponding point to use is at 200 versus 6. So you can divide 2000, sorry, that's 2000. So that is going to be 2000 according to the displacement over 6. All right, so if we divide 2006, this is going to give us a decimal that is 333,33333 and so on, which is in meters per second. Remember, this is velocity. Yes, it's gradient, but that gradient represents velocity, so it is going to be in meters per second. Someone can write this as meters per second like this, still one in the same way. All right, so that was question 5.22. Having 2 marks. On 5.3, we are given that Victor has got a mass of 82 kgs. He travels to Mars. What will his weight be on Mars if the gravitational acceleration on Mars is, so we are given a gravitational acceleration on Mars, okay? So take note, as we are used to 9,8, but in this case, we are given another gravitational acceleration, but we know that weight is not going to change. Our weight is going to be the force, that is the force, but this is the mass times the gravitational acceleration. So it's going to be the mass times the gravitational acceleration, which is going to be 82 kgs. But the gravitational acceleration for Mars is 3,711. So you multiply these two. All right. So that can be your weight in newtons. All right, so let's see if we are to multiply this one, what are we going to have in this case? All right, so I'm just going to show you the screen. So our calculator here, that's 82. So we've got 82 multiplied to 3.711. All right, which is going to give us 304,302. So that's 304,302 Newton. All right, so that is what we are going to have in this case. All right, so if we are to check on question 5.4, we are now given that Peter is flying in a hot air balloon. He drops a sandbag from the balloon and it takes 11 seconds to hit the ground. All right, we are given the time it is going to take to reach the ground. Okay, draw a neat labeled velocity. Take note this time, it's a velocity time. Previously, we drew a displacement time. So this time, we are referring to a velocity time graph, okay? For the falling sandbag, note, use a scale of 1 second equal to 1 centimeter. and we are given the velocity now 1 centimeter representing 9.8 meters per second. Okay, so take note, this guy is going to take 11 seconds when this sandbag is going to take 11 seconds to reach the ground. So we know that our velocity time graph, we are supposed to have, okay, let's just have a sketch here. I'm just going to show you a sketch. Let's just have our ruler so that I can show you the sketch here. So remember, we are dealing with the velocity versus time. All right, so that's question 5.4. So we are going to have our time axis here and our velocity axis. All right, we are going to have our velocity axis here. So that's something of this nature. All right, so if we are to take a closer look in this case, we are given the time it takes to complete movement in this case, whereby our time is given in seconds. All right, so you can just write this. Then later on, this is your velocity in meters per second. All right, so for each time that we are given, for the 11 seconds, we are given that each second is supposed to be represented with 1 centimeter up to 11 seconds. So this is what you're going to do. Each centimeter, that's a 1. So you're going to have 1 centimeter, 1 centimeter, 2, 1 centimeter, each and every centimeter. Okay, so that's 4, 5, 6, 7, 8, 9, 10, 11, each and every centimeter. All right. Then on the velocity, we are given another consideration that every 1 centimeter is 9.8, all right? So every centimeter, that's 9.8 meters per second. So you're going to have 1 centimeter here, which corresponds with this one at 9.8. 1 centimeter, we add 9.8 plus 9.8, which is at 19.6. So this must correspond up to 11. So we must add up to 11. So like we are now at 2, we move on to 3. The third one, we add 19.6 plus 9.8, which is going to be 29.4. We add until the 11th part there on top, okay? So that is going to be 39.2. If we add, that's 49, all right? If we add, that's 58.8, 58.8. If we add 9.8, we are going to have 68.6. If we add 9.8, we are going to have 78.4, and so on, guys, okay? Up to the last one, which corresponds with what? With 11. So that is at 98. And the last one at top, that's 107.8. So it must correspond. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. According to the time, we've got 11 units, 1, 2, up to 11. So this 11 corresponds direct with 107.8. These 2 points, they correspond with each other. Just like what we saw, the points 1 and 9.8, it corresponds 2 and 19.6, and so on. So this point, so if you are to join them now, you are going to have a straight line from the point 0 to the point of intersection. That's from this point, you are going to have a straight line like this one. All right, we are going to have to join from this point. So on your graph, you're supposed to do this accurately according to scale. So here I'm just showing you exactly what you're supposed to have, but you have to do it accurately. All right, so if we are to join these points, this is the gradient, which is the slope. So this time, this gradient or the steepness of the slope, it represents the acceleration. Take note, this is a velocity time graph. So this one, it represents acceleration, which is your gradient. If it is a displacement time graph, the steepness of the slope or the gradient, it represents velocity. So this one, it's a velocity time graph. So it is going to represent acceleration, which is measured in meters per square second. All right, so that was the question. Let's check the other part. Okay, so that was the last part, 5.4, having 3 marks. And to end everything on this question, that is 11 marks. So that was dynamics, guys, from this question paper from Maison African Motives. Till we meet again.